Welcome to AP Chemistry at Hononegah High School. I'm Brian Brown, and today we'll be looking at misconceptions related to the Chapter 10-11 tests. So what are some things that students typically struggle with that you don't want to struggle with? Uh, Number one, same thing as almost every single one of these I've done. You have to watch your units. Be careful. Remember, if you're talking SI, that means you're in kilograms, you're in meters, you're in seconds. So be aware of what you've got in certain problems because it's something that comes up in a number of different situations. One situation, which R value is SI? So when you're looking at our R values, which one we say was SI? Remember, that was the 8.31 R value. Now, one of the things you need to understand is our 8.31 value that we talked about in notes looks slightly different on the AP constant sheet. And that's because they've changed it to what stand out as SI units. They've converted basically the complex unit you saw in the R value we looked at into joules and moles and kelvins. So it'd be joule over mole kelvins. It's the same thing as our kilopascal unit in essence. So those two things are equivalent to each other. So one of the things you have to be aware of is if you want to get to meters and seconds, then you have to use this R value. And one place that comes into play is remembering and calculating RMS speeds. When you're calculating the RMS velocity of a substance and using that equation, it's got an R value there. You need to use the appropriate R value to end up getting meters and seconds. So be careful and be aware of that. So one of those things that you should probably look more closely at is look at that RMS. You did it in your homework assignment, you did it on your review, something you need to be careful with. It's also tied to units on the test. Second thing, understanding boiling point and normal boiling point for as basic as an idea this is, really a vocab idea. There are a number of questions typically students will struggle with. So remember, boiling point is a temperature at which the vapor pressure equals the atmospheric pressure. That's all boiling is. As you increase the temperature of a substance, its vapor pressure is going to rise. When it equals the equivalent pressure pushing down on the liquid, you get boiling. If you're not at that temperature, you don't get boiling. So boiling point really is not a temperature. It's a variety of temperatures depending upon atmospheric pressure. So one thing you need to understand is the consequence. Know that this means that we can play with boiling points as long as cooking times by playing with atmospheric pressure or the pressure above the liquid. So literally walking up and down mountains, changing altitude, well, that has an effect on pressure. That has an effect on boiling point because boiling point is tied to your atmospheric pressure. And if you're trying to cook a food that, it's a soup basically where you're boiling water, well, you can only cook the ingredients inside that water as hot as you can get the actual liquid. So that's tied to boiling point as well. So make sure you understand that concept. Final thing related to this is remember the normal boiling point is basically the temperature when the atmospheric pressure is standard pressure. So it's the same thing, but now we're talking about a very specific atmospheric pressure. We're not changing it. We're looking at a 1 ATM situation. Next idea, heating curves and energy and temperature situation. So I pulled this heating curve right out of the notes because it's nice and convenient. It's also color coded for what we're looking at here. Um, Keep in mind, you need to have a very good understanding of what's happening in this heating curve because you also have to draw them for specific problems, which we'll look at in a second. You need to understand what's happening differently in different parts of this heating curve with energy, both kinetic and potential, and what's happening different with temperature. Why is the temperature remaining constant at times? You need to intuitively understand all these different components here. So first of all, where does the kinetic energy change? Well, notice the question is in blue because that's our blue regions here. Region AB, CD, EF. Your kinetic energy is changing. How do we know that and why? Well, because the temperature is changing in each of these. So really the why is related to when we're dumping in energy in these specific regions, we're speeding up particles. That's changing kinetic energy if we're playing with their velocity. And then where does potential energy come into play and why? Well, that would be at our flat spots here, our changes of state. Now, notice our temperature is not changing. So that means we're going to end up using a different equation when we're calculating those energies a little bit later in this review. But the real question here is why is it flatlining? How come temperature isn't changing? Well, that's because we're not changing kinetic energy. Well, we're still dumping heat in. So if we're not changing kinetic energy, what are we changing? Well, we're changing potential energy. Why are we changing potential energy at these regions? Remember, we are breaking intermolecular forces. And when we are freezing, melting something, I should say, here, notice it's a shorter time frame than when we boiled it. Well, that's because we're dealing with different amounts of potential energy here, partially changing in BC or partially overcoming intermolecular force in BC, totally overcoming the rest of the intermolecular forces in DE. Takes more energy to do that. Next idea, total volume. And this is something you just have to watch out for. When you think it through, it conceptually makes sense, but you really haven't seen this idea too much. So it's something that I really want to make you be aware of. So let's say we've got a chemical reaction like you see here, and we're mixing A and B, and they're both solids. And when we mix specific amounts of A and B, then we're going to make specific amounts of C and D. Well, notice C and D are gases here. So if we've got a problem that asks you to calculate the total volume in a PV equals nRT situation, how is that different? Why is that special? Why do you need to be careful of that idea total volume here? Well, let's say we had 1 mole of A reacting with 1 mole of B. Well, by our stoichiometry, that's going to make 1 mole of C and 1 mole of D. So when A and B react, 1 mole of A react with 1 mole of B, we're making 1 mole of C gas and 1 mole of D gas. Why is the wording so important? Because you need to understand in the process, we're not really looking at, what's the volume of C that we're producing. You need to understand that volume is tied to the number of moles of gas you have. And we have two gases here. Both of them are gases. So they are both going to contribute moles, which when we're doing our PV equals nRT, if we want to get total volume, we have to look at total moles here. So in this particular case, if we establish how many moles of C are being produced, and we know then that it's a one-to-one stoichiometry, we know the number of moles of D that are being produced, we have to add those together to get our total moles. So if you're doing PV equals nRT and you want to get the total volume, you need to take into account that we're looking, or the total pressure even, you're looking at the total moles in this particular situation. So be careful when you've got a reaction, when you're making more than one product that contributes to the moles. Remember, it doesn't matter what kind of substance, it's just how many total moles are you getting. They're going to affect pressure and volume and things like that. Next one, know the 4 types of solids and the differences in their intermolecular force strength and properties, which would be a direct result of that. Now here we're using kind of a loose term, intermolecular force. Intermolecular force normally means these things down here. What we're really looking at in this particular problem is different forms of intramolecular forces. Because when we're looking at different types of solids, we're looking at melting and boiling points as one of our main property differences. Well, it's all about the glue that holds them together. And yes, in a molecular substance, we're actually looking at our 4 intermolecular forces here on the bottom. But in our covalent and our ionic and metallic, what we're looking at when we're going to melt it is overcoming our intramolecular force, not really our intermolecular force. So when we melt water, we are not breaking apart the water molecule. We're partially overcoming the intermolecular attractions, which would be hydrogen bonding, between our ice crystals. So our molecules of ice, I should say. So keep in mind, when we're talking about solids, and we're talking about melting them and their properties, these are really looking at overcoming intramolecular force. This is really looking at overcoming an intermolecular force. Although it would be true when we're talking about breaking a water molecule, we're talking about breaking an intramolecular force. So make sure you have a fundamental understanding of these different types of solids melting and what's going on with really what's happening. Are we breaking an intra or an intermolecular force? And fundamentally know the difference between them. Do not confuse them. Know everything IMF's control. Remember in notes one day I threw up this and said, this is most of the stuff we're going to look at. And then lo and behold, the review comes along and I ask you about some other things. Well, you can apply these same ideas in other situations as well. So yes, you should get all these, but I mean, when you think about it, specific heat is related to how hard it is to change the temperature of a substance. Well, what prevents you from speeding something up? Well, intermolecular forces. So specific heat is also tied to intermolecular forces. There are other things tied to intermolecular forces, and you should be able to apply them. Not just these types of things, but yes, you should understand all of these. In addition to this, so kind of like no intermolecular forces and what they control, part two. When you've got a question related to trying to decipher what's happening with intermolecular forces, and often you're given, boiling points, melting points, any kind of property that you can tie to IMF. If you're looking at that, first think about what that means. Obviously, the thing with a higher melting point or boiling point is going to have stronger intermolecular forces. So think of that straight away, because if you're trying to explain that, it's kind of nice to know what you're explaining. This is stronger. If I know that, it's a little easier for me to decipher why. And remember, we talked about this breakdown. If you're looking at two different things, or even one thing with intermolecular forces in between it, think about whether it's polar or nonpolar, because there's a definite difference in strength off an intermolecular force. If it's polar, remember you're looking at hydrogen bonding or potentially the strength of the dipole. Often we don't really get into this level in the question, but sometimes we do, and electronegative difference can help us see that. So just, in general, where they're on the periodic table can help us. Often it's this is polar and that's got hydrogen bonding or degrees of hydrogen bonding. So you don't see two quite as much here, but it is something you can often figure out. And then finally, nonpolar, remember that's Limpec. And remember, you can't say that on an FRQ. You have to actually spell out what you mean by that. But it is a simple way to think of things. Now, a couple things about Limpec. First off, if the shape between all the substances is the same, they're all a simple tetrahedral, um, they're all diatomic, it's going to be a size Olympic situation. Look at the differences in molar masses, which will be tied to the number of electrons, which will give you larger, more polarizable electron clouds. If they're very, very different in size, so we have some molecular things and they're very different in size, the London force is eventually going to become strong enough that that's really what we're looking at. So if we've got all things with similar shapes, um, but the sizes are fundamentally different, it's also a size impact type situation. Even if we're talking about polar molecules, that would be true. Next, if you've got the same formula but a different shape, remember we were looking at stretching the hydrocarbon out versus having a branched hydrocarbon. That's shape limpak. It's really looking at surface area, stretching it out, larger surface area, so larger, more polarizable electron cloud. And then remember ionic compounds. That's a Coulomb's law type thing. Look at first the charge differences, and then second, look at the size of the ions. Next thing, calculating complex energy problems. Remember, you must be able to draw a heating curve, and we'll practice that here. Now, we're not going to actually get numbers, but I want to walk through all the ideas with you here. So remember, when we have a heating curve, we're talking about, changes in physical changes for a substance. Warming it up, cooling it off, melting it, freezing it, boiling it, all those types of things. Well, there's two different equations that govern the energy in those types of situations here. Sometimes it's mc delta C, and sometimes it's delta H times mass or moles. And remember, unit of this will derive which of those you've got. And be careful, units, watch units, watch units, watch units. I should have put this on that first one. Another situation of watching units. If you're adding two together to get the total energy, and one's in joules and the other's in kilojoules, you can't add them. Get to a common energy. Okay, let's practice drawing one. What would it look like? How much energy would it take to heat H2O from negative 10 to 89? First, you need to establish what's your starting point and what's your ending point. Now, whether you're going up or down. Well, obviously, I'm going from a lower temperature to a higher temperature here. So I'm going to start out my heating curve um, at a low temperature down here. And that's actually, in this case, going to be the actual temperature, negative 10 degrees Celsius. But I'm going to start my heating curve there. That's the point. Now, what happens when I've got something at negative 10 degrees Celsius, H2O? Well, that's ice. And I know ice melts at zero, so first I'm going to go uphill. How far? Don't really worry about that. But that's the first thing that's going to happen here is I'm going to go uphill. Now, something's going to happen different here at 0 degrees Celsius. We're going to start to melt. And remember, at a change of state, we're flat. Once all of it's melted, then it would warm up. Well, we're going to 89 degrees Celsius here. So we're finishing at 89 degrees Celsius. So yes, I'm going to warm it up again. Do we get to another change of state before that? Well, it boils at 100, so no. So I'm just going to go up to that point. So I have three distinct regions here, so I'm going to have to do three calculations and add them together. Now notice I've color-coded things because you have to decide which equation you're going to use where. And remember, if you have a temperature change, like in my red regions here, you're using MC delta T. Be careful, while the mass isn't going to be changing, these two things are probably going to be changing. Specific heat definitely, because solid and liquid specific heats are different. That's because their intermolecular force strengths are different. And Delta T is typically different between the two. Here it's going to be negative 10, or I should say negative 10 to 0 would be a difference of positive 10. 0 to 89 would be a difference of 89. So those two things, watch and be careful of that. And then in our other regions, our flat regions, remember it's a delta H of reaction, just depends on the reaction. Here we are melting something, so we need the delta H of fusion. And if the unit is given as joules per gram, then we're going to multiply by the mass. But we need to get the right delta H. Is it fusion? Is it solidification? Because that would be the opposite of fusion. Is it vaporization? Or is it condensation? Because that would be the opposite of condensation. Be aware of those things in these problems. And once you've calculated your three energies, get them to a common energy unit, and then add them together. Final thing we're going to look at here is manometer, barometer type situation. I only put manometer, but I decided I might as well talk about barometer as well. Remember, what's happening in a barometer is you have a pool of liquid that you put an evacuated tube in that's sealed. In other words, it's not open to anything because the opening is underneath. You don't have anything pushing down in the tube because it's a vacuum inside there. So there's an imbalance of forces here. The atmosphere is pushing down on the rest of that liquid, and where the tube is, it's not being pushed down on. So that's going to force mercury up that tube, and that mercury is going to have a height. And if we've got the right size diameter here, the height of this mercury in millimeters, so we'd be talking about millimeters of Hg, that is a valid way to express a pressure. So that's how we measure atmospheric pressures. We use a manometer. And what we're really doing is we have to have a evacuated tube, and we're looking at the height difference between the two. Because remember, it's going to keep pushing it up until gravity basically stops it from going all the way to the top. So there is a limit to how high it's going to push it up, because gravity also is a force pulling down here. And what happens is once those two forces are equal to each other, it stops moving. Well, gravity doesn't change, but atmospheric pressure changes, so that mercury level can rise up and down. Second one we're going to look at here is an open-ended manometer. Now, in an open-ended manometer, you have exactly that, an open end right here. Well, if it's an open end, you are pushing not only against the height of this column of mercury, but you're also pushing against atmospheric pressure. So that would be why the total pressure of the gas is the sum of those two. Now, when you have a closed-end manometer, what's really happening is this is no longer open. So it's closed at that end. So we no longer have gravity pushing down. And what you're actually going to have inside here would be a vacuum. So the only thing that is fighting the gas is the height of that column. So those are some of the things that students typically struggle with on this test. I hope that helps you to do better. Good luck.